Hey guys, so in this video we will be talking about hash tables. So as you can see, we have a table of grind times, which is a BMX move where you are grinding on a rail with your bike and recording the longest times for 7 days in May um, that we were able to hold a grind rail. So on May 12th, we were able to hold it for 5 seconds. On May 13th, we were able to hold it for 4.8, and so on and so forth. We were able to hold it the longest on the 7th day at 5.32. Now, what we want to do with this data is we want to put it into a hash function. And then from that hash function, we want to put it into a hash table. And right here, I have it illustrated. So a hash table is this whole thing. And as you can see, there are 10 indices. This is one indice, this is two, so on and so forth. And there's a few things to notice about this. First of all, we can notice that the first indice starts at array at 0, and the last array ends at 9. So we always start at 0 when referencing an indice, just like how we would reference the first element in an array. So if we have array 0, we are referencing the first element in the array, which would be, in this case, 3. So that same application is applied to a hash table. Secondly, we can also notice that this indice can also be called a bucket because like 10 buckets, as you can see here, we have 10 yellow buckets. You can put the value associated with May 12th, and from our Excel spreadsheet, we can see 5 is associated with May 12th. 5 is the value associated with the key May 12th. And this value is put into one of these 10 buckets. And it's not put into these buckets by pure luck or pure chance. It's put into a specific bucket by implementing a very specific hash function that will convert this key, which we can consider a string, into a integer that will point to the indice that it goes into. So in this case here, we can see that 5 is put into index 6 because of the hash function. Now, hash functions can be arbitrary, and we're going to go into an example of a hash function. But hash functions can look like anything, and they can do a bunch of different things to output where a corresponding value will go. But the most important thing to recognize about a hash function is that no matter how many times you input May 12th, you will always put its value in the same indice, no matter how many times you run May 12th. So for example, if I run May 12th one more time, where I have May 12th and I put it into the hash function, it will again put 5 into index 6. And we'll look at Jupyter Notebook and see a hash function in action. So before we develop a hash function, let's go over a function, a built-in Python function that our first hash function is going to use, which is ord. And ord will output the corresponding Unicode character for a given character. So say we pass in M in ord, it will output 77. And if we output a character that's not a alphanumeral, we get code. There we go. We get 36. And if we find the Unicode character for a space, which is also a character, we get 32. Now, what's the good thing about Unicode and why it's so effective for hash tables is that no matter how many times we find the ord of a character, we will always get the same number. So it's not random, which means that the key that we pass in, like May 12th, will always have the same Unicode no matter how many times we pass it in. And that's basically what we want from a hash table, right? Is we want a key that's identical to a key before to have the same value go to the same index. The index being the output of the hash function. So let's begin creating the hash function. We will call it hash function. And we'll pass in key. Key is the date, which would be, in our case, something like May 12th or May 13th or whatever. So we pass in May 12th into key, and we will create a variable, initialize it to 0. And for char in key, char is character, and key is May 12th. So we're iterating through May 12th. We will add the corresponding ORed Unicode value into the variable index. So, for example, we start with m being char in key, and m is equal to 77. So 77 is added to index, and then we go to the next character, which is a, and a is 97. So we add 97 to index, which already has 77. 77 plus 97, and then we go on so and so forth, including the space, which has a Unicode of 32. And we will get a really big index value. So if we return index, this is our hash function, and we run the function with a passed in value, which is May 12th, we will get 646. Now 646 should be the index that we put our key into. And from the previous example, if you can recall, we had only 10 spaces in our for char in key. Char is character, and key is May 12th. So we're iterating through May 12th. We will add the corresponding ORed Unicode value into the variable index. So, for example, we start with m being char in key, and m is equal to 77. So 77 is added to index, and then we go to the next character, which is a, and a is 97. So we add 97 to index, which already has 77. 77 plus 97, and then we go on so and so forth, including the space, which has a Unicode of 32. And we will get a really big index value. So if we return index, this is our hash function, and we run the function with a passed in value, which is May 12th, we will get 646. Now 646 should be the index that we put our key into. And from the previous example, if you can recall, we had only 10 spaces in our hash table, and that's optimal. We want as little buckets as possible to make the algorithm more effective. So one way we can reduce this index number is use mod 10, so that when we run it, we get 6, because mod 10 means 646 divided by 10. Its remainder is 6, and that's what mod does, is it finds the remainder of those two divided. So we can do that for the other keys that we have. May 13th will output 7, and we'll do that all the way to May 18th. So May 14th will output 8. May 15th will output 9. Now, what comes after 9? You would think it would be 10, but because we passed in modulus, the possible values that can be outputted are between 0 to 9, right? Because you can't have a remainder greater than 9. So May 13th will output, May 16th will output 0. Similarly, May 17th will output 1, and then May 18th will output 2. And we can see that these indices are incrementing because the only thing we're really incrementing between each total is the one number. And the Unicode for 2, so ord of 2, is 50, and then ord of 3 is 51. And then ord 4 is 52, 53, 54. So that makes sense why the index is incrementing, right? But say we change the th and make it like May 2nd, where n does not have the same Unicode as t and d has a different Unicode than h, then this will output 7, which is also the same index that May 13th goes into. So this whole hash function works, and we will now see how this looks visually. And as you can see, we have the corresponding keys, which are found from here, with their corresponding values, added to the corresponding indices. And just to recall, indices are the output of our hash function. So since our hash function outputted 0 for May 16th, 5.3, which is the value associated with the key May 16th, will go into index 0. And as you can see, it kind of neatly fits into the hash table, which is optimal in that we really don't want a undistributed pairing of values into each indices. So we don't want like 5 values in index 0 and then only 2 values in index 4 and then nothing in indices 6 through 9. We really want it to look something like this, where we have all the values as distributed as possible. And that's where we go into what an optimal hash table size looks like. Optimal hash table size. And in order to find this, we need to follow 2 simple rules. General rule of thumb to choose size of hash table. Table should be an array with length 1.3 times the maximum number of keys. So if we go back to our example, we have 7 keys, right? 7 keys. So 7 times 1.3 equals 9.1. So any number above 9.1 would be a reasonable amount of buckets or indices for the hash table. The second rule, which will optimize it even further, is that the size of the hash table should be a prime number. So combining these 2 rules, we want a closest prime number greater than 9.1, or whatever the key times 1.3 is. So in our case, the closest prime number greater than 9.1 is 11. So 11 would be our ideal size for our example here. And it's based solely on the number of keys that are passed in. So if we have, say, let's say 75 keys, so we have 75 days, an optimal hash table size would be 75 times 1.3, which is 97.5. And then we have to find a prime number greater than 97.5. That's closest to 97.5. So 98 isn't, 99 isn't, 100 isn't. I think it's 101. I'm pretty sure there's no divisors. Is 101 a prime? Yes, it is. So 101 would be the size of our hash table if we had 75 keys instead of 7. So now that we have that established, we can continue on our discussion of hash functions, and we can create another hash function just to show that hash functions can look like anything that we want. And we will go back to the Jupyter Notebook and develop that function. So now that we're back at the Jupyter Notebook, we can create another hash function using a different built-in function. So instead of using ord and incrementing through each character in a string to find the total and then finding the mod, we can use a different built-in function called hash, which will output an extremely large number, and we can do something with this number because hash will remain the same even if we run it again, right? So now let's see if we can identify any patterns with hash so that we can know how to implement it in our hash function. So May 13th also returns looks like 19-digit negative number. May 14th outputs a 19-digit positive number. And then May 15th also outputs a 19-digit positive number. So it's safe to say that hash will output a 19-digit integer, and I say integer because it can be negative or positive. We can start creating our hash function, which should look a little bit simpler because we don't need to add the total of the ord for each character like we did with the last function. So we create hash function 2, and we pass in a value, or let's call it key rather for consistency, and then we say index equals hash key, and then let's use mod 11 since we found that a hash table of size 11 is the most optimal size for 7 different keys, and then we can return index, and let's see what we get. Hash function May 12th, it should be 2, and we get 7. So index 7 will contain the value associated with the key May 12th, and the key of May 12th is, I think, 5 point something, I forgot, but we can do the same thing for May 13th, and it outputs 3. So it'll go into index 3. May 14th will output 10, so it'll go into index 10. And note that 10 is a viable index because we have 11 as the mod, so we effectively have 11 different indices or buckets, with 0 being the first and 10 being the last. And then we can do that for 15th. We get 7. So this is interesting because now the value for May 15th will go into index 7, which actually collides with the value associated with May 12th, which also goes into index 7. And optimally, we want as little collisions as possible because we want it to be distributed as evenly as possible. And especially with this optimal hash value, it shouldn't happen as frequently, but we'll see if we get any other collisions. May 16th outputs 2, so that's a new indice. May 17th is 6, and then May 18th is also 6. So we have 2 collisions for 2 different dates. Cool. So now that we created the hash function, we can go back to the drawing board and finish our discussion on hash tables. So that should wrap up our discussion about hash functions, hash tables, and key and value pairs. And note that we did all of this in Python, and key value pairs are also a key component of dictionaries, and we've been actually using the dictionary terms this whole time to implement this hash table and hash function. Hope you guys enjoyed the video. This is a very introduction, I guess, to hash tables, and hope to see you in the next video where we can talk about more complex ideas, and we can talk about collisions, and we can maybe even go through interview questions related to hash tables. Thank you for watching, and see you in the next video. Peace.